Hello, my name is Kevin Starr. In this episode of Single Loop Control Methods, we're going to talk about what happens when you're dealing with cycles. Things oscillate. How's control work in that framework? Up to now, we've talked about step changes. If I change the set point or I have a load change in a step, we know how to calculate that. We're going to review that here. But what happens if the cycle is in the disturbance? What happens if it's an oscillation? Well, what's going to happen? Can control fix it or not fix it? That's important in today's industrial processes. Very few things just move in a step. Everything oscillates. And that's what we're going to try to identify, is by finding out what the controllable energy is for your signal, you can troubleshoot and know whether it's a control problem or a process problem or a header problem, and you can do an awful lot by understanding the concepts of control as it applies to cyclic reduction. Now, in the world of process control, we talk about set point changes and disturbance. So those are both forms of regulation. So if the operator changes the set point, we want the measured value to get there. If the set point's flat and the process moves, we want it to get back. So they're both a form of regulation. And we've been talking in terms of steps. I have a step change or a step disturbance. Well, what happens if I have a cycle? We're going to focus primarily on cyclic disturbance, and we'll talk on both of those as we move through. Here's an example that we've talked about, is where I change the set point. You can see my measurement. Let's assume we got a first order process, or we've tuned it to be a first order process. So it's going to roughly take 4 closed loop time constants for the measurement to settle out at the set point. Here what we have is disturbance that may go through the process. It can happen at either sides, but where it takes 4 time constants to come back. So that's kind of understood. If I have a step change or a disturbance change, it's going to take 4 time constants to get back. This is just illustrating the difference if a disturbance goes through the process or happens at the measurement. This one's a lot more abrupt, but it still takes 4 time constants to come back. But what happens when we have a sine wave? That's what I find fascinating in this, is if you've done any signal processing or studied signal to noise ratios or done stuff with a cell phone or listen, in the world of phone, we don't want to hear that. We just want to hear the voice. So we want the signal to be amplified, which is our voice, and you want the background noise to be as small as possible. What's interesting in process control, we actually want noise. A signal is an oscillation. We don't want oscillations. We want to track those down and find them. So if you're familiar with signal conditioning or signal, how to deal with filters for noise suppression, it's literally a mirror image of that for process automation, and that's what we're going to talk about. But just to define some terms, we're looking at a sine wave. A sine wave is defined as a periodic signal that repeats itself after a period of time. So that time is called a period. So in one period, the sine wave will repeat itself. And you can see that it has an amplitude, and sometimes they'll call it peak to peak. So we have an amplitude and a period, and so that's a sine wave. So you can look at, a lot of times I'll have to ask, are you talking about peak to peak or amplitude? But it's going to have an oscillation or a sine wave look to it. Now let's step back a second and take a look at this signal. We're just watching a signal, just sort of ebb and flow here. Can you deconstruct it in your mind? Can you see if this is my signal off control and I were to remove the noise? Here's the noise, and here's the low frequency component. So if you in your mind could add those back together, can you see how you could get the total signal? That's what we're trying to do here. This is sort of an academic exercise, is you've got to deal with all of it. But if you can imagine deconstructing the signal into the low frequency and noise components, we're getting closer to being able to identify what control can deal with. So now if I turn control on, what's control designed to work on? Is control designed to fix the noise or fix the low frequency? It's designed to fix the low frequency. So that's what control has to do. It has to look at that disturbance, reflect it into the actuation device, like the shock absorber, and try to reduce the intensity of that disturbance as it moves through. One of the benefits, a huge benefit of the direct synthesis tau ratio tuning that we talked about, is you can actually calculate the point at which, in the frequency world, that a controller's ability to regulate stops or gets tremendously attenuated, and we're going to look at that. Here's an example. Now let's say we have 2 controls, the same disturbance. On this case, we have a fast loop. Remember how we defined fast? A tau ratio of 1 or even less than 1. so as compared to the open loop time constant. And here we have one where the closed loop time constant is slow, so it's 3 or 4 times. So you can see where I changed the set point and it shoots right up there on the one on the fast. On the slow, it takes a long time. So which one of these do you think will do a better job with that disturbance? Well, over here, this is our disturbance. If we turn control off, that's what we get. Now here, if we turn control on, can you imagine the valve doing something like this to make that error go to 0? What we've been able to do is the disturbance is slow as compared to the tuning of the loop. So the loop has time to make the actuator move in such a way to absorb it. It's a lot like your car. If you have a bumpy road and your shock absorbers, you want to have the frequency such that you don't feel anything, but your shock absorbers are banging around to try to keep you from feeling it. That's what a control system is doing all the time. The shock absorber is your actuation device. And so if the road is moving slow enough, you don't feel it. If it's too fast, it passes through and you get to feel it. And that's what's happening on this side is the disturbance, even though it's the same disturbance, it's now too fast for this control to deal with. So when control tries to deflect the energy into the valve doesn't move. So if a valve doesn't move, the off and the on control process is about the same. And so what happens is if you're in a driver, you think your shocks just broke, or the terrain is now rougher than your shocks can absorb. Where does that point happen? Where do we go from a fast loop tuning that can fix it to a slow loop tuning that can't? The other thing is often we don't have one disturbance and 2 tuning techniques. It's usually the other way around. We've tuned a loop a certain way, but we have a whole array of disturbances that get thrown at us. And that's what we're looking at here. Is on the left we have a very slow disturbance compared, if you look at this is a tuning that we picked, they say a tau ratio 2.5 or 3. So over here, for a slow, if the disturbance is slow as compared to the tuning, I can redirect it into the actuation device so that the on-control process doesn't see it. However, on the right side, my oscillation is fast. Notice it's going up and down before this thing even had a chance to think about it. So it literally passes through the controller and the on-control process sees it. Have you ever seen that? A lot of times people will say, oh, your control's causing that. Oh, but look, it's attenuating it a little bit. So is it working or not? And then people will go retune it. Maybe that's not the problem. Maybe you have a disturbance that is passing through your controller. And the real trick isn't to retune it, it's to go find the source of the disturbance and fix it there. That's what's the beauty of what we're about to talk about is if you know how you tune the loop, you can calculate the point at which your controller's ability to attenuate goes away. And then it's process design, and that's what gets to be fun. So this picture also kind of illustrates what's happening is the disturbance. Remember, this is a feedback control system. So this actuator has to move fast enough to counter the effect of this disturbance. If the disturbance is affecting the process, it has to generate an error. Then the controller has to think about it and make a change in the actuation device. If this disturbance is oscillating too fast, this thing can't adjust the actuator fast enough to stop the disturbance. So you can see what happens. In this case, if it's a low frequency disturbance, it's being passed and we actually have time in the feedback path to fix the problem with the actuator and compensate for it with the actuation device. And so it doesn't show up in the process. That's the feedback. Feedback is slow by nature because of this feedback path. I'm not going to talk about it here, but feed forward is a compensator that will basically measure this disturbance and change the actuator in proportion to the disturbance so it doesn't have to go through this path. That's a different discussion, but just so you can see where we're headed. Right now we're trying to fix this through the feedback path, and if you have a cyclic disturbance, it has to be fairly slow as compared to the dynamics of this loop, otherwise the disturbance is going to pass through. Now, let's define some terms. There's a thing called amplitude ratio. This has its roots to Bode plots and the frequency domain, and we're not going to go into that. We'll show you some examples, but the amplitude ratio is a way of measuring the attenuation characteristic of your controller. So for example, if I turn control off and it's sitting there oscillating, measure the amplitude. So here I've got, say, an amplitude of 10. It's oscillating, I got an amplitude of 10. Now let's put it on control and see what happens. Here we got an amplitude of 5. So what happened? So we can say that the controller was able to redirect 50% of the energy into the actuator. Okay, so we have an amplitude ratio of 0.5. So that's a measure. So you just measure your off control amplification or amplitude and your on control. So there's really three choices. One is if it passes through, off control and on control will be the same, 10 and 10. So what would your ratio be? 1. Well, what happens if it comes out higher? Let's say it's off control is 10, you turn control on and it comes out at 20. That means you're amplifying it. That would be bad. And what happens if it comes out at 1? Well, you're attenuating it. So you either have a pure gain where it passes through 1 to 1, you have an amplification, or you have an attenuation. Those are really your three choices. So let's talk about that. In an ideal attenuation curve, now imagine if you could do this, is you set up a signal conditioner and you could cause your process to change a really slow frequency and then you get faster and faster and you can measure it. That's not really possible. In some of the simulators we have and in some of the labs we actually do that. But I want to show you the ideal example. Over here we have this point beyond which our controller can't do anything. So if the frequency is low, very slow, as compared to how we're tuning it, the attenuation of that loop is nearly 0. That means it gets 100% removed. Okay, so you can see if it went in at 10, it came out at 0. So the ratio is 0. Over here, if the frequency is very, very, very fast, if it comes in at 10, it's going to go out at 10. It has a ratio of 1. So if we were to plot the ideal attenuation curve, it would start off here in the high frequency at 1, and there would be a point at which it would be 0. This is called ideal. This is what that point is what's referred to as a break point or a cutoff. It's also referred to as a knee, and I'll show you why here in just a minute. But the idea here is you can have an amplitude ratio in the low frequency range that you want to be as close to 0. That's our goal, is we want to remove oscillations. That's why tuning a loop faster has a big impact on this, and I'll show you that in a minute. An amplitude ratio of 1 means the signal passes through. And if the amplitude ratio is greater than 1, that means that we're adding energy to this signal every time it goes around. And we want to avoid that because that's not good. The problem is, think in terms of potholes in your road, and or lumps in the road, and your shocks are, if they're 2 feet apart, you don't feel it. But if it's, a foot and a half apart, all of a sudden you feel it. It's just not physically possible for you to go from, let's say I have a disturbance right here, just to the left of the break point, and it says, oh, okay, I move 100% of it, and now I'm on this side, and 100% of it passes through. That's just not reasonable in the world of first principles. There has to be a gradual change, and that gradual change looks like this. And this is what you'll see in terms. This is called a Bode plot, B-O-D-E, Bode plot. But just right now, I don't want to go into the math behind how this is calculated, but notice the scaling looks kind of funny. This is called a logarithmic scale. But again, I wanted to look at the key points that we're looking here is at the cutoff period, 70% of the signal stays. So that you're only attenuating 30%, 0.3. And every time you go 10 times away from the cutoff, your attenuation drops by 10%. So this is a common attenuation curve when we tune a loop to be a first order closed loop response. That means that at the cutoff, you're attenuating about 30% of your signal, and then every time you move a decade away, your attenuation drops by 10%. So the idea here is if I have a disturbance, I want my cutoff period as far away from it as I can get because that's when all the attenuation takes place. Now it's kind of complicated, but I've got an example we're going to run through. So this is showing 3 different cases, A, B, and C. And what we could show here is I've got cyclic disturbances at A. It's sliding through, it's slow. Notice the frequency. We're starting off very slow. Low frequency, it was over here. This is low frequency, like say at A, B, and C as we pass through. So look what happens. At A, it's low as compared to how this loop is tuned, and it's attenuated highly. B, it's a little faster, so you can see a little more of the curve comes back. C, it's really fast, and it almost nothing passes. This doesn't mean the control's bad. It's doing everything it can do. This is where I see problems, is people see this oscillation, oh, your loop's causing me problems. Well, it may be just passing the signal through, and the problem isn't even that control loop. So by understanding how to calculate this cutoff period, you can quickly, if you know how you tuned it, and you can look at the oscillation, and if you can see it's there, you can say, oh, you know, this is how this loop's tuned, I need to go fix the source of this. Or if we should be removing it and we're adding it, then I know I've got a tuning problem. So very quickly you can identify, do I have a tuning problem or a process problem? Now, what's interesting here is as you change your tuning, you actually change your ability to regulate cyclic energy. So here what we're showing is if we used a tau ratio of 1, we might have this kind of a curve. If a tau ratio of 3, you can see what happens. So here's a question. What does a tau ratio of 5 look like? How about a tau ratio of 10? How about if I turn the loop off, what would this look like? As you turn a loop off, this line goes flat. Maybe that's obvious, but the ability of your controller to regulate is gone when the loop's in manual. So a loop that's in manual or a loop that is very, very, very slow can only deal with very, very, very slow oscillations. Now, the consequence isn't always true either. You know, we're saying, well, if a tau ratio of 1 is this good, let's go with a tau ratio of 0.1. That's where we'll get into nonlinearities, but not everything's a first order process. And as you get more and more aggressive on your control, those assumptions that we made about the process start to get bad, and all of a sudden you get what, if I were to draw, you get this big spike in the AR curve, and you can cause a loop to go unstable. So that's why we like tau ratios of 2 and 3. They allow us to absorb our uncertainty so that we don't amplify, but we have to recognize where the frequency band is. And that's what I want to show you an example. So here, if you did a bump test and you got a first order response test where you had a process gain and a time constant. Remember the definition of tau ratio. It's your desired closed loop divided by your open loop. And we picked 1, 2, 3, or 4. 4 was slow, 1 was fast. So this is the process. If we plug it into this equation, here I'm showing an example where my time constant is 6. I just picked time constant of 6. So you did this bump test and this had a time constant of 6. Notice that at tau ratio of 1, 2, 3, and 4, my closed loop time constant is 6, 12, 18, and 24. And my cutoff period is this equation right here. It's 2 pi, remember pi is 3.14. 3.14 times your closed loop time constant. Again, that's just the math behind it, and maybe in a future episode we'll talk about the theory, but for right now this is just a rule that if you've come up with whatever your closed loop time constant is, which is your tau ratio times your open loop time constant, you multiply it by 2 pi, and that's the point. That's called the cutoff period. At that point, you'll 70%, you have an AR of 0.7. That means if it comes in at 10, it'll come out at 7. Okay, so you can see here we're at 37, 75, you know, if our time constant is 6. Here's the example. Here's 2 examples where I've tuned a tau ratio of 1 and a tau ratio of 3. Here if I change the set point, you can see that it's got a time constant of 6, and here's got a closed loop time constant of 18. If we have a step disturbance, I just overlaid all of them on top of each other. So you can see that's what's nice about the direct synthesis technique, is that the set point disturbance, the set point change and the load disturbance, they act the same way. So if I have a tau ratio of 1, the mirror of that is the disturbance. Tau ratio of 3 is a set point, the mirror of that's the disturbance. So that's what we're starting with, and that's what we've been talking about if I do a step change. This is important to do that as a validation step. After you've done your bump test, your visual inspection, your bump test, your modeling, you came up with your tuning, you change the set point, this better be what you get. Once you have that, you can also calculate what the frequency range that controller is designed to work on. So here's an example where we plugged in a low frequency oscillation. So here you can see this is in manual. If I flip the control off, this was my disturbance. And then when I tune it at a tau ratio of 1, you can see I'm right here, and a tau ratio of 3. Remember, it's slower, so more of the signal passes through. Here what we did is at a tau ratio, we changed the frequency, so now we're faster. So you can see at tau ratio 1, we're still attenuating more than a tau ratio of 3. And then here we got a really fast signal, and we're now a tau ratio 1. Now, is the control failing? No. we're just following this curve. And I've always kind of liked this picture, is it shows at what our disturbance regulation looks like at different frequencies. So here, this is a tau ratio of 1, this is the tau ratio of 3. So you can see at a tau ratio of 3, because the frequency is fairly slow compared to the way the loop was tuned, it does a pretty decent job. But then as we go faster and faster, even at the fast loop, the disturbance passes right through. And this is a frequency that control can't fix. So you can't, there's a limit. You can't just keep tuning the loop faster and faster, otherwise you'll make this go worse. So what do? That's where you sit down and you look at your P&ID drawings, you talk with your customer and try to figure out where is this disturbance coming from. And then there's a whole nother set of analysis. But the ability to be able to say, hey, this is not a control problem, this is a process problem, is huge. And if you flip the control off, you'll see the amplitude get bigger. So those are what I'm getting at, is by understanding this general picture, by knowing that you can calculate this cutoff period. You don't actually do this test, you don't send in oscillations, but knowing the frequency band because you applied the direct synthesis tuning technique is huge. I've used it several times to troubleshoot process. I get called in, the loop's oscillating. I say, well, this is it's approximately got this time constant, and I can say, let's flip it to manual, and if it goes away, I know I've got a control problem. But if it's still there, it's a process problem. It's not control's fault. So we can know how a loop's tuned. And a lot of times when people are doing tune by feel, they get slower and slower and slower. And what happens is this curve gets straightened out. So a loop that's turned off and a very, very slow loop have the same ability to regulate, which is 0. So as you tune a loop on, that curve comes down. But there's a point that it'll start to amplify. So that's why we recommend tau ratios between 1.5 and 3. That way you don't over amplify uncertainties. And that's what we'll get into when we get into dealing with dead time. So in this particular talk, we talked about dealing with cycles and oscillations and trying to identify that frequency that control can design. 2 pi times the closed loop time constant gives you a number that you can decide if it's to the left of that, it's good. If it's to the right of that, it's going to pass through. That's dealing with cyclic disturbances.